Hello guys, welcome back to another video. In today's video, we'll be learning convolution neural network. And we'll not just learn convolution neural network, but we'll also create our model using the convolution neural network architecture. So if you haven't watched my previous videos, then I highly recommend you to watch my previous videos because this video is a continuation video from those videos. So let us quickly recap what we did in our previous videos, and in case you don't want to watch my previous videos and you just want to learn about convolution neural network, then you can download the code I'll provide you in the description box. So let us quickly recap what we did in our previous videos. So in our previous videos, we imported the dataset, which is FashionMNIST dataset. So FashionMNIST dataset contains 28 by 28 pixels grayscale images, so which are the images of clothes. Then what we did was we visualized our dataset using matplotlib, and then we created train and test data loader. So we created train and test data loader because we cannot send like thousands of images to our model at once. So it will be computationally inefficient. So to solve that problem, we created data loader. So data loader are like batches. In one batch, you have certain number of images. Like in our case, we have 32 images in one batch. So what we're doing is, instead of sending 1000 or like thousands of images through our model, we're just sending batches of our images. So at one time, we're sending 32 images, and we'll then let the model work. So this will solve the problem of computational inefficiency. And then what we did was we extracted image from our batch, and then we visualized our image, and then we created our base model. So our base model was fairly simple model. So we flattened the data, we had linear layers, and then what we found out was that our model result was not good. So we can see that the model loss was about 50%. So our model was doing as good as predicting, and also the accuracy was pretty high, but the model was struggling to make predictions correctly. And then what we did was we improved our model by adding ReLU activation functions. So ReLU is a activation function which helps us to learn nonlinear patterns in our images. So after training our model by adding ReLU function, we can see that the model result was not that good. So in fact, the model loss increased from 47% to 48%, and model accuracy decreased. So we found out that adding ReLU activation function would not work. So in today's video, what we'll be doing is we'll be building convolution neural network. So convolution neural network are neural network that are specifically designed to work with images. So let us understand what is convolution neural network. And for those people who already know what is convolution, what is polling, I recommend you to skip this section and then follow along the next section, which is the coding section. But for those who want to know more or do not know about convolution and polling, watch this section and then we'll code our neural network. So let us understand what is convolution. So what you see here is this matrix. You can assume that this is a image. So image has pixels like this, and each pixel has some certain numbering. So if some pixel has like 30, it means that pixel is bright. And if some pixel has value 10, then it means that pixel is less bright. And by combining less bright and more bright, you can form image patterns, and that eventually forms the whole image. So you can consider this as an image. And then in convolution step, what we do is we apply a special matrix, which is also known as kernel matrix or kernel filter. We apply this kernel filter to our image. So why do we apply kernel filter to our image is because we want to extract important information from our image from different reasons. So to extract important features or shapes, curves from different portions of our image, we apply a special matrix called kernel matrix to our image. So how do we apply this kernel matrix to our image? So what we do is, applying means that we will do dot product of this kernel matrix on our original image matrix. So after performing dot product, we'll get something like this. So what is happening behind the scene is that, let me annotate so that you can understand quite well. So okay, so this is our kernel matrix, and then what we're doing is we're applying this kernel matrix in this region first. So what is happening is 0 times 10 plus -1 times 20 plus 0 times 30 plus -1 times 10 plus 5 times 20 plus -1 times 30 plus 0 times 20 plus -1 times 30 plus 0 times 40, and this result will be 10. And similarly again we'll apply this kernel matrix to another region, which is this region, and then we'll perform dot product and we'll get this number. Then we'll apply our kernel matrix to this region and then we'll get this result. Again, finally we'll apply our kernel matrix to this region and then we'll get this result. So by applying kernel matrix to different portions or different regions of our image, we are extracting important information, and we'll get a special matrix which is called feature matrix or feature maps. So these are feature maps. So this feature maps represents important information from our images or image. So that is what happens in the convolution step, and this is all that happens in the convolution step. In convolution step, we want to extract, the whole intent of applying convolution step is to extract important informations from different regions of our image. So maybe in this portion of our image, maybe there is curves or there is points. So we want to identify these patterns. So to identify these patterns, we build a special matrix called kernel matrix, and then we apply this kernel matrix to different regions of our image, and finally we get a special matrix called feature maps, and this represents our image. So after convolution, what we do is polling. So this is an example, and here the image matrix is smaller, the dimensions are small, but real images, they have very high dimensions. So our feature maps will also be generally of high dimensions. So polling is a step that reduces the dimensions. So it is responsible for reducing the size. So let us suppose this is our feature map that has been extracted by applying kernel matrix to our image tensor or image matrix. And in polling step, what we do is, the whole intent of polling step is to reduce the image dimensions. So currently we can see that this image has 4 rows and 4 columns. So this is 4 by 4 matrix. So what we want to do is, we want to reduce this to 2 by 2. So we want 2 columns and 2 rows. So what we do is, we do something called polling, and there are different polling methods. One polling method and most commonly used polling method is max polling. So let us apply max polling in this image and let's see how polling works or max polling works. So let me remove this annotation. Okay, so max polling, what it does is that firstly we go through 2 by 2. Okay, first we go through this region. We can consider this region. Okay, from this region, what is the maximum number? 50. So we get this number from here. And then what is the maximum number from this region? 110. We get 110 from this number. And then what is the maximum number from this region? 20. And finally, maximum number from this region is 40. So the whole idea of polling is to reduce the dimension. So from each regions of our image, we extract the most important feature or most important feature from different portions of our image. So from this region, from this portion of our image, the most important thing that we need is something that we have extracted here. So from each region, we extract important information, and then we only want to feed this important information to our model. So we don't need some noise portions of our image. So finally, after performing convolution, where we extract important shapes, curves from different portions of our image, and then we reduce the image dimension, we get we get an image which looks something like this. And this image now represents important information of our original image and also has its dimension reduced. Now this is the image that we want to pass through our model. So that is all that happens in convolution and polling step. So now next step, let us look at the bigger picture. So firstly, what we do is we have an image tensor, or we have a image matrix. So we are using PyTorch, and in PyTorch we have tensors that we feed into the model. So I might say word tensor or matrix like irresponsibly. So this is our image tensor. And then what we do is we apply convolution step. In convolution step, we get different feature maps. Now this feature maps has important information from this image. And then after convolution process, we do polling. In polling, we reduce the dimensions of our feature maps. So something that we just seen before, we reduce the dimensions of our feature maps. And then finally what we do is we flatten these images, the final images, into a single dimensional vector. So this is a long one-dimensional vector, and then we feed this to our model. So first, convolution, we extract important information. These are called feature maps, and then these feature maps are very high dimension. So to reduce the dimension, what we do is we do polling step. Now we reduce the dimension, and then we flatten out our result, and then we feed this result to our traditional neural network. So let us look at another example. So matrix, we go through convolution step, and then we go through polling step where we reduce the dimension. Again, we go through convolution, and then again we reduce the dimension. So convolution and polling can happen iteratively. So each time we're extracting important information from our image, and each image we are reducing the dimension. And then finally we feed this one-dimensional vector to our traditional neural network. So this is what happens in convolution and polling step. So if you understood the theory, now let us see the practical implementation. So we will understand step by step about convolution and polling. So first of all, before building our model, let us understand convolution and polling by code. So first of all, what I'm going to do is I'll create a random tensor. So first of all, let me connect my Google Colab to the runtime. Okay, my Google Colab is connected to the runtime. Now let me execute all the cells. So I'll execute all the cells before the current cell. Now what I want to do is, I want to code out how convolution and polling process occurs. I want to demonstrate how this process is occurring. So what I want to do is, I want to create a random image batch, and then I will send that image batch through convolution layer, and then I'll send the result from the convolution layer. I'll send that to the polling layer, max polling layer that we just discussed. So let me wait until my whole cells run. Okay, all my cells in the Google Colab has been executed. Now let us, in implementation, let us see how convolution and polling process is occurring. So let me create a random image tensor. So I want of the size, let's say I want 32 images in one batch, and 3 color channels, 64 by 64 dimension. So these are my height and width. This is my color channel, and 32 is the batch size. So in one batch I have 32 images. So let me store in the variable test image batch. So let us extract the first image from this batch. So test image equals to test image batch, and I want the first sample from this first image from this batch. So let me run this cell. Okay, so it's not random, it's rand-n. Okay, let me run this cell. Okay, so let us see our test image. So we can see our test image is a tensor. So this is 3-dimensional tensor. So what I want to do now is that I want to send this test image through convolution layer, and I want to demonstrate all of this that I just talked about. So let us create our convolution layer. So to create convolution layer, we have NN module from Torch library, which we have already used in our previous chapters. So let us create our convolution layer. So nn.conv2d, and then what we have to do is we have to pass several parameters. So first parameter is in channels. So in channels is the color channels. So in our case, the color channels is 3. So 3. And then out channels. So out channels is how many output we want from our convolution layer. How many feature maps. So let's say I want 10 feature maps. And then I have to define the kernel size, which is the size of this filter called kernel matrix. So let's say I want 3 by 3 kernel matrix. So I can just write 3 and it will be just 3 by 3 kernel matrix. And I have to define stride. So stride equals to 2. So stride means how many pixels you want to sift the kernel matrix when applying through your image tensor. So if the if stride is 1, then first of all your kernel matrix is applied in this region, and then it sifts one stride here, and then it applies kernel matrix in this region. In our case, stride is 2, so which means that first it is applied in this region, and then it sifts 2 pixels there, and then it applies to the next pixels. So stride equals to 2, and then we want padding equals to 1. So padding is like we want like outside one pixel from every dimension. So we want to capture as much information from our image. So this is our convolution layer, and then let us store this in the variable conv layer. So we have created instance of our convolution layer. Our convolution layer takes 3 channels, which is the color channels of our image: red, green, black, red, green, blue, red, green, black, RGB, right? Yes. And then the out channel represents the feature maps that we want to generate from this layer. And then kernel size is 3 by 3 kernel matrix, stride 2, which means that we want to sift 2 pixels to the right. And then padding is 1, which means that we want to capture more information, how much more information we want to capture. So what I want to do is I want to pass my test image through this convolution layer. So conv layer, and then let us pass our image. So our test image. So let us store this in the variable conv result. So let me run this cell, and let us print the shape of our test image first. Image dot shape, and then let's print the shape of our conv result dot shape. Okay, we can see our the image was 364, 3 color channels, 64 height, 64 width. And now after passing this image through our convolution layer, it has 10 out channels, which is it generates 10 feature maps, and also it decreased the height and width. So it's now 32 pixels height and 32 pixels width. So after our image has gone through convolution layer, now our image has the dimension of our image has decreased, and we have feature maps, like we have 10 feature maps that contains important information from different regions of our original image, which is the test image. So now let us pass the result that we obtained from the convolution layer to the polling max pool layer. So let us create a polling layer. So nn.max pool 2d, and we have to define the kernel size. So kernel size is 3, and let us store this in the variable pool layer. Now through this poll layer, we want to pass the result that we got by passing our image through convolution layer. So pool layer, and then let's pass our image or feature maps, which is conv result, and then let us store the result in poll result. Run the cell and let us visualize the shape of the image that we obtained after passing through polling. Save. Okay, poll result. So we can see after passing our image through convolution layer, the height was 32 pixels and the width was 32 pixels. But then after passing our 10 feature maps through polling, we have obtained that the height is 10 pixels and width is 10 pixels. So the dimensions of our images have been reduced. So let us again summarize what is happening behind the scene. So we generated an image which has 64 by 64 pixels heights and width respectively. And then we passed the first image from this batch through convolution layer. So by passing our image through convolution layer, it generated 10 feature maps, which is what we defined while creating the instance of conv2d. And we can see that the dimension reduced to 32 pixels and 32 pixels heights and width respectively. Then we passed the result obtained from conv layer to polling layer, which the polling method that we're using right now is maxPoll2d, which means that from each 3x3 dimension of the image, we are extracting maximum number. And what we're doing is we're passing the result obtaining which we obtained from convolution layer to max polling layer, and then we can see that the dimensions of our image has been reduced drastically. So I think you understood what was convolution layer, what was polling layer. Now let us do the most important thing, which is building our convolution neural network for the data. Our data, which is FashionMNIST data. Okay. So let us create the neural network, which is convolution neural network. So let me add a text. Create convolution neural network. Okay, so of course we're going to use the class approach, which is we will be using nm.module as our superclass, and we'll be creating our convolution neural network model. So class, let us name this as FashionMNIST model v2. The previous models were v1, v0 and v1. So let us name this as FashionMNIST model v2. And we will be using nm.module as our superclass. And then let us create constructor. So def init, so self, and then the input we need is input shape, so which will be of type integer, and then we need hidden units, which will be again of type integer, and then we need output shape, which will be of type integer. So let us call the superclass constructor. So super dot underscore init. So now what we want to do is we want to have several blocks of our convolution and polling process. So let's define our first convolution block. So conv block 1, and we'll be using sequential, which means that we will sequentially define the layers in this block. So first sequence is we will be applying convolution. So conv2d. Here the in channels will be, of course the in channels will always be 3, but in this case we are passing the input shape from while we instantiate this class. So in channels will be input shape, and then we'll have out channels, so which will be hidden units. Again, we'll pass these parameters while we instantiate this class. And then let us define kernel size. So let us create 3x3 kernel matrix, which means that we'll apply filter matrix, which is kernel matrix, 3x3 kernel matrix to our image. And let us define stride as 1. So which means that we shift kernel matrix 1 pixel each time when we apply the kernel matrix, or when we apply the convolution process to our original image. and then let us also define padding as 1. So this was our first convolution layer of conv block 1 part, and now let us create a ReLU. So we want to capture non-linear patterns. So what ReLU does is it will filter all the negative numbers, and then it will only let positive numbers to pass through this layer. So that is why it helps to learn non-linear patterns. Now again, let us again create another convolution layer. So first of all, we're passing our image through convolution layer. We capture the non-linear patterns, and again we pass the output to another convolution layer. So in channels, this time should be the output from this layer, which is the in channels should be hidden units. So hidden units, and the out channels from this should be again hidden units. And then we need kernel size. So let's keep same as previous 3, and stride as 1. We want to shift 1 pixels, and then padding as 1. So again, let us learn nonlinear patterns, which means we have another activation function, ReLU activation, and then finally we apply pooling process, which is max pool. So max pool 2D, and we need to define the kernel size. So kernel size, let's define 2 this time. Okay, so in our convolution block 1, we have our image passed through convolution layer, and then we pass through ReLU, and then we pass through another convolution layer, we pass through again ReLU activation function, and then finally we pass through max pool 2D, where we are decreasing the dimension of our image. So this was first convolution block. Let us create another convolution block. So I will just copy and paste this here, and this will be convolution block 2, and everything else will be the same. So first of all, we pass our image through this block, and then again we pass image through this block. So each time we're extracting so important features from our image, and then each time we're reducing the dimensions of our feature maps. So finally, after passing through convolution blocks, now finally we want a classifier, which means we want our regular neural network. So self.classifier equals another sequential, and then remember what I told you, we need to flatten out the output from this after passing through convolution and pooling. So let us create a flatten layer. So nn.flatten, and then what we need is we need a linear layer, which is our regular neural network, or regular output layer. So the in features, so this is the most confusing part. So how many features will this layer take? So we do not know, because our image has passed through so many convolution and pooling process that we do not keep track. We do not have track of our of input shape that we need to pass through this linear layer. So for now, let us experiment this. So let us keep something as 8. So let us experiment this. For now, we are keeping the input features as 8 in our linear layer, but obviously this will change. We'll identify the shape, and then we'll later on fix this. So another thing we need is output features. So output features will be my output shape, which I will pass while I instantiate this class. And then another thing that I'll need is that I need to create a forward method. So as I'm using nn.module as my superclass, I compulsorily need to create a forward method which defines the forward pass. So self and x is going to be the data that I need to pass through my model. So first of all, what I'll do is I'll pass my data through conv block 1, and I'll store the result in variable x, and then again I'll pass the result that I get from conv block 1 to conv block 2. So self dot conv block 2, and let us pass the result from conblock1, and then again let us store the result in variable x, and then finally we want to pass through classifier, so self.classifier, and let us pass the result from conblock2, and we want to return the result. Okay, so this was our model. So in our model we have convolution block 1, convolution block 2. Each convolution block has several convolution layer and a polling layer, and then we have a flatten layer, and then we have a regular output layer. So we're passing our image through conblock 1, through conblock 2, and then finally we're passing the result to our output layer. So let us run this. Now let us create instance of our model that we just created. So FashionMNIST model v2, and then we need to pass input shape. So again, input shape would be the color channel. So in this case we have one color channel in our FashionMNIST dataset, because FashionMNIST dataset is a grayscale image. It contains grayscale image. So hidden units, so let us keep as 10. So by passing hidden units as 10, what we're doing is we want in first block we want a convolution layer to have 10 feature maps, and so on. So hidden units equals to 10, and output shape would be the length of class names. So if you want to see what is class names is a list which contains all the classes of FashionMNIST dataset. So these are the images, sample images that is present in the FashionMNIST dataset. So the length of our class names is 10. So we're passing output shape as 10, and then finally what we want to do is we want to pass our model to the target device. So our target device is CPU right now, but in your case it might be GPU, you might be using CUDA. So let us store in model, store the instance in model 2. And by the way, we have already defined agnostic code in our previous chapters, so I highly recommend you to watch that. But if you can see, the CPU currently we have is CPU. The device we currently have is CPU. So let us run this. So we have created our model 2. So now what I want to do next is that my model is in target device. So I also want to send my model parameters to the target device. So model2 dot parameters, and I want to send this to the target device. So what I want to do is next. So I want the first one, and then let me send this to the target device. Okay, so my model is now in target device, and also my model parameters is in target device. So let us visualize our model. Yeah, so model 2. So again, we can see that first block is convolution block, second block is another convolution block, and then we have the regular neural network. So now what we want to do is let us test our model by passing some random data. So before passing our real data, which is the FashionMNIST dataset, let's pass a random test data, and then let's visualize how our model is working. So let me add a markdown, creating a random tensor like our real data, and finding out the shapes of the model. So you can remember that here we passed 8, which was completely experimental. We need to again redefine this input feature in features. So let's test our model, and then let's fix this. So now what I want to do is, let me create a random tensor. So torch.randn, and then size I want is batch size to be, okay, color channel to be 1, and then 28 by 28 pixels. And then let me store this in the variable random tensor. So let us visualize the shape of a random tensor, which will of course be 128 28, but just for the sake. So okay, 128 28, which means one color channel, 28 by 28 pixels image. So what I want to do is I want to pass this random tensor through my model. So let us pass this random image to our model. But again, before doing that, what I want to do is I want to visualize how my model is working. So what I want to do is I want to print the shapes after my image passed through each block. So x.shape. So let us add a print statement. Okay, let us add a print statement. Okay, image, let us say data after passing through conv block 1, and it would be x.shape. And similarly, I want to see how the shape looks after passing through conv block 2. So data after passing through conv block 2. And then finally, okay, let's do this much. So let's run this. So okay, let us pass this random tensor to our model. So what I want to do is model 2, and when I pass my some data through model, this function will be running. So, and from this function we call different blocks. So what I want to pass is I want to pass my random tensor. So random tensor, but this would throw an error because we have an extra dimension. So to get rid of this extra dimension, I will unsqueeze this. So unsqueeze is a function or a method that will get rid of extra dimension. So unsqueeze 0, and then also I need to send my data to the target device. Okay, so let us run this cell and let us visualize the shapes. Okay, FashionMNIST forward function. Okay, it says forward function is required, but I have already defined the forward function. Okay, this should be one step outside. Okay, the error we are getting is because we have a slight mistake here. So we have defined input shape as the in channels for this block convolution layer. So this should be hidden units because the output is coming from the previous block. So this should be hidden units. So let us run this. Okay, so we can see after our image passed through convolution block 1, the shape is 1, which is the batch size. Then my convolution block 1 has produced 10 feature maps, and then 14 by 14 pixels. And then after I pass the output from conv block 1 to conv block 2, the shape is again 1 batch size, 10 feature maps, and then the size has been reduced to 7 pixels. So now what I need to do is I need to fix the input in features for this linear layer. So the in features should be 10 times 7 times 7. So that should be hidden units times 7 times 7. So my hidden units times 7 times 7. Okay, let us run this and let us again visualize this. Okay, now we don't get error, and we can see that after passing through the linear layer, the output is like the model has given me the probabilities for 10 different classes. So from here we can see that although this was a random data, my model predicts that the image was likely to be this first class, which can be any one of those. Okay, so we have visualized how our model is working. Now what we want to do is we want to pass our real data through our model. So this was just a test. We have fixed our model, so this is going to be our model. Now let us pass our real data. So what I want to do is, first of all, I want to define loss function and optimizer function. So loss function equals to nn dot cross entropy loss. So cross entropy loss has softmax function applied internally. So I don't need to apply softmax function again. and then I have optimizer. So again, what loss function does is it calculates how bad my model predicted. And let us define optimizer. So torch dot optim dot we're going to use stochastic gradient descent, and then I need to pass my model parameter. So my model is model 2 and parameters, and then also I need to define learning rate. So again, this is a hyperparameter. Let us define 0.1 for now. So now what I want to do is, let us train our model and then let's test our model. So we have already defined functions for training and testing. So if you want to look at that, so okay, this is a function for training our model. So we send the data to the model, then we calculate the loss, and then we perform backward propagation. We then update the gradients, then we calculate the average train loss and test loss, and then we return the average train and test loss. And similarly for testing, we do the same but for test data. So we have already defined the function, so this should be fairly simple. So torch.manual seed. So let us create a reproducibility, so next time we get the same result. So 42, and I want to train for 3 epochs, and let's keep track of time. So time equals to timer. Let us run our train and test model functions. So for each epoch in TQDM, so TQDM is used to visualize the progress of our model. It gives us a very good progress bar and range epochs. So we want to run for 3 epochs, right? So let us create a print statement. So which epoch we are currently on. So let us visualize that epoch, and then let us call our train model function. So train model, and then we need to pass several parameters like the model. So this is model 2, data loader, so train data loader, and then loss function would be my loss function that I just defined, which is cross entropy loss, and I need to pass optimizer, and then I need to pass the accuracy. Okay, I need to pass accuracy function. So we have already defined accuracy function before. So accuracy function just calculates the accuracy, like it compares how many my model predicted correct, and then it returns the number. So accuracy function, and then we need to pass the device, which is the target device. So this was for training. Now let us also call our test model, which is the function to test our model. So we need to pass our model data loader, test data loader. Again, if you want to look how I created the train and test model functions, I highly recommend you to watch my previous videos. So loss function, we need to pass loss function, which is loss function, and then I need to pass accuracy function, and the target device equals to target device. Okay, so let us print something like this, so that for each epoch we have a separation, and we have a start time, so I need to have an end time as well. So end time, timer, and then let us print train time. So again, print train time is a function that takes end time and start time, and it calculates the difference between the time. So in this way I know how long my model took to train. So start equals to start time, start time, and then I need to pass end time, which is end time, and then I also need to pass my target device. So okay, so when I run this cell, my model should train, it should test, and then it should print the train and test time. So before doing that, what I want to do is I need to comment out this code so that the print statement does not look so messy. Okay, so first epoch, so training is happening on first epoch. So okay, this progress bar that you're seeing right here is because I have used TQDM. So let us wait for a few time, and I'll be back when the training and test is completed. Okay, we can see that my training and testing has been completed. So let us see how my model performed. So in the first epoch, the train loss was 59% and the test loss was 40%, and the train accuracy was 78%, but my model performed well on test data. In second epoch, it was 35%. So my train loss decreased, which means my model is going on the right direction. And also my test loss decreased. And the train accuracy increased a lot, like from 78% to 87%. And also my test accuracy increased a bit. And the final epoch, my test loss came down to 31%. So my model is going on very good direction. And the test loss also came down to 32%. The train accuracy finally has 88%, so a good progress, and the test accuracy is 88%. So okay, my model is going on the right direction, and the model that we created, this convolutional neural network, is working as expected. So now what I want to do is I want to evaluate my model. So before evaluating my model, what I want to do is let us evaluate on the first image of our train features batch. So if you want to see what my train features batch contains, so train features batch. So if you look at this, my train feature batch contains all the batches of training. So from this, I want the first batch. And also, let us visualize the shape. I want you to visualize the shape, and also I want the first from train labels batch. Labels batch. I want the first one. So dot shape. So for those who have watched my previous videos, I think you should be familiar with this. So for those who haven't watched my previous videos, train features batch contains all the training images samples, and train labels batch contains all the samples of labels. So here what I'm doing is I'm extracting the first image and then the first label from the first batch. So train features batch, and we're visualizing the shape basically. So we can see we have one color channel, 28 by 28 pixel, and then why did this came? Okay, we don't need to do shape actually. This is obviously one dimension, so not even one dimension. It should be a vector. It should be a scalar, so which means 5, which is the target. So let us pass this image through our model, and let us evaluate whether it predicts the same. So let us evaluate our model. So we need to put our model to evaluation mode. I believe we should make a function for this, but let's just go like this. So torch.inference mode. So inference mode. So inference mode will disable gradient tracking, because while evaluating our model, we do not need to track the gradients. So let's pass the train features batch, this first image, through our model. So let's pass this to our model, and obviously we need to get rid of this extra dimension. So on squeeze from the 0th dimension, and then let us send our data to the target device, because we've put our model to the target device. Our model parameter is also in target device, so the data that we send through our model also needs to be on the target device. And my model will obviously give the logits, which are raw numbers. So y logits. So to convert the logits into prediction, so I can do is ylogits dot argmax. So this will give me the index that has the maximum value. So I need to pass the dimension parameter, dimension equals to 1. So let me run this, and let's check if our model predicted the same or not. So ypred, fingers crossed. Okay, my model predicted the same that I expected. So my model accuracy has been justified. So 88% accuracy. So let us we have created an evaluate model function. So let us store the results from the evaluation and then let us visualize the result of all the models that we have created. So let me call evaluate model function. So my evaluate model function will take model. It will take a test data loader because we want to evaluate using test data. So test data loader, loss function is equals to loss function, and then accuracy function. Okay, so evaluate model will give me a dictionary, and let us store this in the variable model to results. So if you want to look how my evaluate model looks like, I have created the function in above here. It should be somewhere right here. Evaluate model. Okay, so this is the function evaluate model. So evaluate model will take model, it will take test data, and then it will return a dictionary containing model name, model loss, and model accuracy. So we have stored the dictionary in model to results variable, and let us print model to results. Model to result. Okay, so evaluation is happening, and we can see that FashionMNIST model v2, which is our convolution model, has loss of 32% and accuracy is about 88%. And let us visualize, create a table using pandas, and then let us visualize all the results from our previous model and this model. So import pandas as PD. So I want to store the result in compare results, and then pd.dataframe. So I want to visualize in table format, and then I will pass model 0 results, model 1 results, and then finally model 2 results. Model 2 result. Let's do results product. So model 2 results, and then let us print compare results. So you can see my first model had loss 47%, but then we decreased the loss and finally came down to 32%. So we've gone through each process, and then we've finally created a model where the loss is low, and the accuracy, we've increased the accuracy to 88%. So we've gone through each and every process. We've created these 3 models. The first 2 were experimental, and then by analyzing these 2 models, we created a final convolutional neural network model where now we know that this model is the best model that we have created. So what I want to do now is that, okay, let us also visualize a training time. How much time it took to train our model for each of these respective models. So I want to add a new column in my compare results. Training time. By the way, we have already finished the model creation. We have already tested our model, but now we are visualizing how our model performed. So right now we are visualizing how our model performed, and then we want to visualize how all the 3 models performed and how we came down to developing a model where the accuracy was high and the loss was low. So training time, okay, let us visualize. Before this cell, I want to add a code. Code cell where I want to see model 1 results, model 0 results, model 1 results, and then finally model 2 results. I haven't kept track of training time. So what I want to do is I want to see from the beginning. So okay, this was my model 0 and the training time was model training. Okay, the train time was 24 seconds. So train time was 24 seconds. So first train time was 24 seconds. We could have tracked this, but now let us do manually. So for first model, the train time was 24. Okay, this was for 24. Okay. $24, and for model 1 the training time was, again for model 1 also the training time was 24 seconds. So it was 24 seconds again, and then finally for our last model the time was 124 second, which is the maximum. Okay, so let us add this column and then let us again see our table. So for model 0 training time was 24 seconds. For second arm model the time was 24 seconds, and final model it took a lot of time, but obviously the model loss came a huge margin down and the model accuracy was 88%. So this is justified. So now what I want to do is I want to compare all the model results. So I want to advance a bit from this table and let us visualize this in diagram way. So compare results dot, I want to set the index. And then what I want to do is I want model name on the y-axis, and then in the x-axis I want the model accuracy. So I want a bar chart where I can see my model performance, and I want a kind to be bar horizontal, and let us create x label. So in my x there will be model accuracy in percentage, and then plt dot y label. In y axis it will be model name. So let us print this. Okay, model name okay, this should be the same. So this should be small. Model accuracy also should be small. Okay, model accuracy, this should be underscore. Okay, so we can see our first model the accuracy was more than about 82%, and the accuracy for model this model was the same, and then finally we had a model which the accuracy was the highest. So okay, so let us again visualize more in more better way. So what I want to do now is I want to make predictions. So this is the fun part. I want to make predictions on my test data. I want to see how many it predicts correctly. So I want to make a function called make predictions. So let me add a markdown, make predictions with our best model. So what I want to do is I want to create a function which will take a list of data, which is going to be images, and I want the function to give me the prediction images. And then what I'll do is I'll compare if the images that the model has predicted is correct to the image that is actually the real value. So what I want to do is I want to create a function, make predictions. I want model, so this should be of type torch.nn.module, and another thing I want is the data, which will be this type, and I want device, the target device. The type should be torch.device if I'm not wrong, and let us give a default value. So let us track the prediction probabilities in a variable predprops. and I want to send my model to the target device. So this is device agnostic code, and let us put our model to the evaluation mode, and let us turn off context managers. So inference mode is a context manager which will turn off gradient tracking, and let us loop through the data list. So for each sample in data, we get access to a single sample, and then what we'll do is let us unsqueeze the data, because we know we want to get rid of the extra dimension we have in our data. So unsqueeze from the sample data, and dimension equals to 0, and then what I want to do is I want to send the data to the target device as well. So let's store this in the variable sample, and now let us send this data to the target to the model. So we're invoking the forward function in the model, and the model will give me logits. So these logits are pure numerical, like raw numbers. So what I want to do is I want to convert these logits to prediction probabilities. So I will use softmax activation function. So I'll pass y logits, and then again I want the extra dimension that I got read in the beginning. So torch.squeeze. So this will add extra dimension, and I want to perform softmax in the 0 dimension. So this will give me prediction probabilities. And then I want to append the prediction probabilities to this list. So predprops dot append predprop, and then we'll send this to CPU. So why we're sending this to CPU, you will know this just a little later, but we're sending this list to CPU because we want to visualize using matplotlib. So finally our model, our function should return the stack. So what I want to do is I want to stack the prediction probabilities on top of one another. So torch.stack predprops. Let us run this. So let us call make predictions function, and then let us see how well my model performs. I will import random test samples. Let me define an empty list, and then I want test labels as empty list. For each sample label in random.sample, so I have test data. So if you want to see this, test data is something that I imported from FashionMNIST dataset. It contains 10,000 data points. So what I want to do is I want to convert the test data into list, and from the test data I want random 9 samples, and then this will return the sample and then label. So I want to append sample to test sample list, and then I want to append label to test labels. So test samples dot append the sample, and then test labels dot append label. So let us run this, and then what I want to do is let us visualize our test samples and test labels. So test samples, so we can see that test samples is a list. Let us visualize first 5. Okay, so test samples is a list which contains all the image tensors, and then similarly test labels is a list which contains labels for all the test all the image tensors. So let us visualize this using matplotlib. So I am show So test samples. So I want the first sample from test samples, which is the first image tensor. And then of course I want to get rid of, I want to add extra dimension, and then CMap equals to gray, just for proper visualization. And then I want the title. I want to index through my class names, and I want the test labels, but again, test labels, but we need the first index of test labels. So let us run this, and okay, so the first image in my test samples is a bag, and the test label, we can see it's a bag. So we've visualized our image. So now let us use make predictions function, and let's see for the same test sample if it predicts a bag or not. So I want to invoke my make predictions function, and I have to pass model, which is going to be model 2, and I have to pass the data, which is going to be test samples. So I'm going to pass the entire test samples list, and then I want to store the result from make predictions in pred results, and let us print the result. Okay, so for each, for all 10 image tensors, this is the result. So what I want to do is I want the maximum arguments, so I want to convert them into classes. So pred results dot argmax in the first dimension. So this will give me the prediction classes. And okay, now I want to compare if my prediction classes is equal to the test labels or not. So let us print the test labels first, and let me print pred classes. Pred classes. Okay, so you can see the prediction. These are the actual labels, and this is my model prediction. So my model has predicted the first image correctly. It failed on the second image. Third image it predicted correctly. Fourth image it predicted correctly. The fifth it predicted correctly. So from here, the only wrong prediction is the second image. So my make predictions function is working correctly. I want to visualize this furthermore. So I want to again visualize all the 9 images, and I want to see which it predicted right or wrong. So let's visualize this more in a more better way. So plt.figure, the figure size is 9 by 9. So I want the figure size to be 9 by 9, and in each rows I want 3 figures, and rows 3 figures, and then I want 3 columns. And let us create a loop. So I and sample in enumerate test samples. So what enumerate does is it will create a tuple. So I would be the index, which would be integer, and then the sample would be obviously it would be the image tensor. So let me create a subplot. So plt.subplot, and I have to pass the n rows and columns, and each time I want to go one step right. And let us print the image. So my image is so sample is my image tensor. So I want to squeeze, which means I want to add my extra dimension, and then CMap equals to gray. So what I want to do is I want to show green color for right predictions and red color for wrong predictions. So for that I need to keep track of the values it predicted correctly and the images it predicted in wrong. So what I want to do is I want to index through class names, and test labels I. So this would give me the truth label, and then what I want to do is I want to keep track of the predicted label. So pred label equals to class names, and this should be pred classes, and then indexing through each and every pred classes. So I want the title text, so let us format the title text. So actual would be truth label, and then the predicted would be pred is the pred label. So let us add a condition. If pred label was equal to the truth label, which means my model predicted correctly. So I want to show the title as title text, and let's specify font size as 10 and color as green. So for all the right predictions, I want the color to be green, and if it predicted wrong, then plt.title title text title text, and then I want the font size to be 10 again, but I want this time the color to be red, and of course I want to turn off the axis just to make sure that my picture looks clear. So let us run this and let us see the prediction of our model. So okay, out of all the images, my model predicted the second image, which is the actual label was shirt, but it predicted t-shirt/top, which was confusing. So we can see my model has predicted one wrong. So let us again run this again. So let me run this again and let's visualize it again. Okay, this time my model predicted all the images correctly. Let us run this again. I love learning. I love seeing my model performance. Okay, this time my model predicted two images wrong. So it was shirt, but it predicted t-shirt/top. We know it's going to struggle in this. So again, it was shirt and it was confused on t-shirt/top. So obviously in t-shirt and top shirt it is confused. So I hope you enjoyed this video. I hope you understand what is convolution, what is polling, and I hope you learned to experiment your computer vision projects. So I would say this computer vision is all about experimentation, all about getting errors, all about identifying flaws in your model, and then finally coming up with a model that predicts correctly. So I hope you learned about convolution, and I will give access to the code in the comment or description. And obviously this video we didn't look at the training function because we created that in the previous video. So if you want to look at how we created those functions, then please watch my previous videos and you would understand everything in this video perfectly. So again, so if you have been here at this point of this video, then please like this video, subscribe, comment, and let me know in the comments what video you want next. Thank you for watching.